these three talks are about questions which are not properly handled by mathematics at this point, but one hopes to improve them. I talked about linear response, then I talked about turbulence, and the next thing I will now talk about life. Now, turbulence, everybody can see what it is. It doesn't mean that it is easy to make a theory. And life, everybody knows what it is, but it's also not obvious how to make a theory about that. Now, let me try to spend some time explaining why there is such a difficulty to understand life mathematically. Now, life is about chemistry, and in fact, far from equilibrium chemistry. So it's about chemical reactions. There are some other things peripheral to it, but basically life is about chemical reactions, and chemical reactions often are far from equilibrium, and that's the case about chemical reactions which take place in living organisms. Now, there are, it doesn't mean that everything is possible. There are some basic rules of physics that have to be respected, conservation of energy, but mostly increase of entropy. So entropy has to increase, and there's nothing, I mean, life does not cheat with that. What life does is it may take entropy from some place and move it to some other place, increase the, as soon as the entropy of the universe is increasing, that's satisfactory, even if some part, some living organism has an entropy that decreases. So entropy is basically, is the up to logarithm, the volume in phase space, and the fact that energy, that phase space volume is conserved is part of the basic equations that are respected for life. If you think of classical theory, for quantum theory, there is something analogous. So at this point, I think there's no difficulty in accepting the fact that the entropy increases. Okay. Now, however, living organisms usually do not work in a space in which the energy is conserved. They work in a situation where the temperature and the pressure are fixed. Now, this is something that has been well understood by people in statistical mechanics. The fact that if you have a volume in phase space that is preserved, or in fact increased because of reshuffling the phase space. So, I mean, what Boltzmann understood very well is that if you have some part of the volume in phase space at fixed energy, it may be convoluted very much so that it becomes dense in a larger piece of phase space, and that's what is the increase of entropy. So that I hope this is clear. Now, what happens is if you want to study life, you do not work with fixed, with an isolated system at fixed energy. You impose a temperature and a pressure. And that means you have to make some change of variables so that you describe a system in terms of different variables. But all these variables are related, and in fact, the fact that the entropy increases means that some quantity called Gibbs free energy, which is appropriate when you study systems at fixed temperature and pressure, that this decreases. So that means that if you are going to survive, you need to get energy from free energy, if you like, from the outside world. Eating and getting this energy from the outside world is in fact increasing the entropy of the universe. It's a different way of expressing the same thing. So I think this is important, otherwise, I mean, the fact that you need to get energy from the universe is equivalent to the fact that you want to throw entropy away. But the two things are in some sense equivalent, and I shall not go into great details about that. But I am trying to fix the language. Now, there has been a paper by Mr. Jeremy England, which has had quite a bit of, I mean, there has been quite a bit of interest in this paper. This paper is called Statistical Physics of Self-Replication, and it uses some statistical mechanics to explain that living organisms, if they are successful, want to throw away to the rest of the universe a lot of energy. So the fact that this was essentially rigorous argument, but involving not microscopic things, but relatively large objects like self-replicating bacteria, attracted quite a bit of interest. And the discussion is not completely terminated at this point because I mean, it's somewhat difficult to understand the basic principles. Now, as I said, life is about non-equilibrium, in fact, far from equilibrium chemical reactions. And what do you know about this? Well, somehow you must increase the entropy of the universe, and that means that you must get energy from the universe. But if you look at definite, well, there's a basic fact about chemical reactions, which is that it's very difficult to predict the rate at which a chemical reaction takes place. If you take sugar and in the presence of air, it would be natural to have a reaction of oxidizing the sugar, but it's a slow reaction, and in fact, if you take a box with sugar, leave it in your cupboard, it will not oxidize very rapidly. On the other hand, you can accelerate the transformation, the oxidization, or whatever other chemical reaction if you have a catalyst. So there are these things called catalyzers that can multiply the speed of reaction by very large powers of 10. And it's very difficult to make a theory of these things. Okay, so that's a fact. The fact is that chemical reactions far from equilibrium are central to the understanding of life, and it's very difficult to predict the rates at which they take place. Now, if you look at the details of a functioning living organism, what it does is it has a complicated system of chemical reactions whereby some chemical reactions which are useful to life are accelerated by appropriate catalysts, which are in fact proteins, enzymes, and other things which are also favored on grounds of on energetic grounds do not take place very rapidly. There's in most organisms something called ATP, and this is used to have all kinds of reactions take place. It provides energy to have all kinds of useful reactions taking place, but in the human organism, it lives for half an hour. It does not disintegrate rapidly. It releases energy where needed and under the influence of catalyst. Now, you see that living organism is an improbable thing where energy is conserved, entropy increases, but the way it is done is very clever in the sense that there are catalysts, namely enzymes, that do make things to occur where they should occur, and otherwise things do not occur. So energy, if you like to speak in terms of free energy, is obtained from the environment and channeled in a somewhat improbable way with these very complicated enzymes to do exactly what they should do to have a living organism. Now, when people realize that, they thought that the thing was so improbable that apart from the fact that we know that there are living organisms, it is very unlikely that life should exist because if it were not for this complicated arrangement, of building proteins, which are enzymes, which are used for life in a certain manner. So then very respectable people found that, life is very unlikely to exist. Or there must be some miraculous, improbable event that created life. So that's an interesting problem. How does life originate? Now, there has been some progress in this. The problem is by no means solved, but at least one sees some way in which the improbability of the origin of life is somewhat mitigated. In fact, what the life that we see, in fact, is we owe the energy to the sun. The sun is used by green plants to provide, to create carbohydrates and so on. And then this is eaten by animals, etc. However, people now tend to believe that the life originated in vents at the bottom of the sea. So there are places at the bottom of the sea where there is communication between the water of the sea and the chemicals that it contains and the deeper layers of the earth, which are in a violently non-equilibrium situation. Basically, one is, if you go sufficiently deep, you will find iron and, in fact, high temperatures. And iron is a very reducing substance. When put in contact with water, it will probably give iron oxide plus hydrogen, which is a reducing substance, etc. So the situation of animals at the surface of the earth, which is now surrounded by oxygen, that is not how life originated. In fact, oxygen came into be a major component of the Earth's atmosphere only late in the history of life. And if we want to understand the origin of life, we have to think of a very different situation, very reducing, hot, and where energy was obtained from chemical reactions, not from the sun. Okay? So what is good about that is that in the situations that one sees in hot water with sea chemicals and interacting with iron and so on, is that these are conditions in which chemical reactions which are chemical reactions which are favored are different in this sort of environment from what we have now at the surface of the Earth in oxygen-rich environment. And things, reactions which are now very improbable and have to be obtained by complicated enzyme reactions could take place in an original environment more rapidly. It doesn't mean that one has a complete understanding of what did take place, but at least things appear less difficult. So that was a sort of digression to introduce the subject of how can you understand life using statistical mechanics, which is the appropriate branch of science to study things far from equilibrium. Now, the fact that you put a name, non-equilibrium statistical mechanics, far from equilibrium, does not mean that you understand anything. The name non-equilibrium statistical mechanics covers some areas which are well understood, namely close to equilibrium, and far from equilibrium, you are basically without much theory. And this explains why you cannot really predict what will be the effect of catalysis on the reactions that take place. So the situation seems to be slightly hopeless, and one reason this paper by England brought quite a bit of interest is that he uses something called detailed balance. Now, detailed balance is a relation. I mean, it can be presented in all kinds of different ways, but it gives a relation between the probability that K goes, that J goes to K, divided by the probability that K goes to J. So when you have a collision of two chemicals that give two different chemicals, or three, or whatever, you can look at the inverse reaction. And there is a relation between these probabilities. And in fact, the detailed balance says that the probability that in time t you go from K to G to J divided by the probability that you go from J to K, this is exponential. Beta is 1 over the temperature. G of K minus G of J. G here is the Gibbs free energy. Now, understand that we are speaking, that we are using variables which are appropriate for fixed temperature and fixed pressure, and those are called free energies, whatever that is. And what is behind this is that these are the appropriate quantities that replace the entropy or the volume in phase space.
There's no t on the right. So you say the probability on time t, but there is no t on the right. It's independent of t.
Oh, okay. So, yeah, that is true. If you wait for sufficient time, this so there is indeed no time on the right-hand side.
So it's an asymptotic relationship, time.
That's a time-independent relation, yes. And this remark that compare with Landauer's principle. Landauer's principle is something that says how much energy you have to spend if you want to erase a digit in computation. But so if you don't know about it, never mind. So this relation says what is the appropriate mixture of J and K that you find when you have equilibrium. Or in fact, it is not equilibrium, but a non-equilibrium steady state. So this relation is interesting in the sense that you do not claim that you will compute the speed of this reaction J to K, but only a ratio of speeds. So if you introduce a catalyst, you will increase the speed at which this reaction goes, but you will also increase the speed at which the opposite reaction takes place. So this is a result which is much safer to use than computations of speeds of reaction. Now, what is involved, and so let me say what is the basis of this relation. The basis of this relation is that you assume microscopic reversibility. The laws of physics, the microscopic laws of physics, should be reversible with if you change the direction of time. So more precisely, if you change the velocities of all the particles involved at a certain time, then the system will go back to its initial state. Is that clear? So that's a fundamental fact about the equations of motion that are used, that are considered to underlie chemistry, and that's a very safe fact. So the notion is that because of this safe fact of the reversibility of the equations of motions, you can relate the speed at which a certain chemical reaction takes place and the speed at which the opposite chemical reaction takes place. This is not totally, I mean, there is some subtlety in that, in the sense that when you went from the entropy to these new variables like the Gibbs free energy, when you look at a chemical reaction taking place in water, the density of the various chemicals in the water is part of the definition of the free energy. So if you have a very dilute J, I mean, if you have a J which has a great density and K which is very dilute, this will tend to push reaction this way. So the steady state which is achieved, and I'm careful not to call it an equilibrium because it's not an equilibrium, but this steady state which is achieved does take into account the concentrations of the various chemicals. And so that's the usual detailed balance, and I'll come back a little bit to the proof of this. It is based on ideas which are unfortunately not completely formalized. No, the fact is that equilibrium statistical mechanics is a very good theory. It is essentially a mathematical theory, and the equivalence of ensembles, the fact that you can equivalently speak of the entropy at given energy or the free energy at given temperature. This is something that is well understood. It involves some assumptions on the interactions between particles. For instance, if you have particles which are purely attracting each other, which is the case of gravitational interaction, one speaks loosely of a gas of stars, etc. However, the laws of equilibrium statistical mechanics do not apply to a gas of star. This is a complicated business and far from understood, but equilibrium statistical mechanics works well for the sort of interaction which is assumed to exist between chemical species of various kinds. Namely, you have repelling at close distances and attraction at somewhat greater distance. And there is there's a quantum version of equilibrium statistical mechanics, which fortunately one can to some extent ignore because quantum effects tend to be unimportant, or at least qualitatively you don't need to understand them. However, equilibrium statistical mechanics deals with particles which have given interactions, and gives different descriptions corresponding to different so-called ensembles, and where you can translate from a description in terms of entropy to a description in terms of free energy. But among the assumptions that are made, you are thinking that the particles that you consider have infinite lifetime. They are stable quantities. Now, however, if you want to understand life, you have to deal with unstable things. So you have to be able to say that a bowl of sugar has a certain temperature, even though this is a difficult statement to the extent that the sugar is not a stable quantity. So if you waited for sufficiently long times, then the sugar would probably give some other take some other chemical aspect which would be at equilibrium, which sugar is not. Now, you want to speak about sugar as it is and to speak about its temperature, and this involves approximations which are not well, which one does not dominate at this point. So equilibrium statistical mechanics is fine, it's a beautiful theory. To apply it to life, you have to stretch the notion of a particle to accept unstable particle or metastable particles. So one has to extend statistical mechanics, include metastable states, and however, then to obtain the theory that we want to have, detailed balance, we have to use this time reversal symmetry. Now, the beauty of detailed balance is that it applies to systems far from equilibrium. If you wanted to deal only with systems close to equilibrium, you couldn't deal with sugar because it's not close to equilibrium. So we'll accept that one can deal with these approximate non-equilibrium states which have very long lifetimes. Now, from the point of view of theory, detailed balance is often derived on the basis of stochastic dynamics. And this means Markovian stochastic dynamics, namely the systems have no memory. Now, this, I think, is a weakness. You can derive all kinds of results with stochastic Markovian dynamics, but the reality of reactions taking place in the real world is not Markovian. So it is desirable to have to obtain detailed balance in a way which does not involve too much of stochastic dynamics, Markovian character, although one would accept some mixing dynamics and local equilibration. So this is why I mean that one does not have a good mathematical theory, but one has some idea how one deviates from a purely mathematical theory. The conditions on the dynamics are weak, but one obtains no prediction on reaction rates, only prediction on some ratio of reaction rates. Okay, so outline of proof. One probability of going from J to K is in fact a conditional probability. It is the probability that you have J at the initial time and K at time tau later, conditioned on the probability that you started with J. Now, this term here, rho of kj times k circle f tau, is by invariance under time reflection the same thing as the same quantity for the reaction going in the opposite direction. Therefore, the ratio of these two probabilities is in fact the ratio of two simpler probabilities, the probability that you are in J and the probability that you are in K. Now, the probability is in fact volume in phase space, or ratio of volume in phase space. And it turns out that in the formalism of fixed temperature and pressure, this is proportional to the exponential of minus the free energy over kT. And therefore, you get detailed balance. That's the normal way to get detailed balance, in which I'm looking at system J and a system K, which do not interact with an environment. So the next thing to do is, so the idea of England is to apply this to biology, to use for the states J and K states of macroscopic states. I mean, bacterium is not really macroscopic, but it's large with respect to the atomic dimensions. And so this is a new idea to use detailed balance for such large objects. And that's, there's nothing wrong with detailed balance being applied to large objects. Can you get something out of it that is of interest? Now, the form in which that detailed balance is obtained by, is used by England is that this ratio is greater than or equal to the exponential of minus the change of entropy minus beta times the change of energy. So the energy given to the environment. And what England claims is that the heat, or should be called enthalpy if you want to use the technical language, transferred to the bath in the transition J to K. So what England says is that if a bacterium is to be successful, namely to replicate rapidly, it has to throw away, other things being equal, a lot of energy to the environment. Now, the slight difficulty is other things being equal.
The equation star is a claim.
Sorry?
The equation star, this equation over there, this is his claim, this equation. So that equation about active bath, the one that is with the star, this is the claim that he's making.
It is the, this is, no, you want to have J to K being large, and therefore the opposite reaction being of small probability. And the claim is that this will be very small if the entropy thrown into the environment is large. Other things being equal, and that's what is slightly delicate. Now, I've here used a form of detailed balance, which is an inequality rather than an equality. I'll come to that in a moment. So now let's look at the situation where we have interaction of a bacterium or whatever with the environment. And so the situation is J goes to K with a certain alpha in for the environment, giving alpha out for the environment. Now, the probability that J goes to K is a sum over various channels alpha going from in to out. And there are the inverse channels. And one can obtain a detailed balance relation for each channel where one reverses the alpha to minus alpha, and that is equality where delta J is the change of free energy of the bacterium, and delta alpha J is the change of free energy of the environment. Okay? So let's define a probability of channel alpha as the probability that it goes via alpha to sum of all probability, the sum over all channels. Then there is some rather trivial calculation. The probability that K goes to J is equal to a sum over the inverse channels of, now we use this detailed balance to obtain the next line. And therefore, you get this equality for J for the detailed balance with a sum over probabilities of the various channels. Now, you can, because of the convexity of the exponential, replace this thing for any choice of probabilities by an average inequality, which is the thing that is used by England. So I have written the free energy in terms of entropy and energy, enthalpy given to the environment, but let me not go into that. Now, one can look at the probabilities for the inverse processes, and there is this relation that gives the P alpha inverse in terms of the P alpha. And one finds that in every situation involving a very large object like a bacterium, these probabilities are not at all symmetric. When you go from alpha to minus alpha, you get something very different. The one thing that is important for alpha becomes negligibly small for minus alpha, which puts some doubt as to the real usefulness of the equation for situation of a bacterium. Still, it is not incorrect, and it goes into the direction of indicated by England. Now, the central point is to prove, in this derivation, the central difficulty is to prove detailed balance in terms of each channel going from alpha to minus alpha. And the idea is to use, so without chemical interaction with the environment, there is no difficulty. If there is an interaction with the environment, then one has to introduce a numerator and a denominator, and as in the other case without interaction with the environment, what comes out is a quotient of things relating to J and a thing related to K with the free energies of the in and out things, and one gets indeed this relation. So
N alpha, you have d alpha and alpha. D alpha is the probability multiplied by E and then alpha.
So this is the change in the environment.
I was wondering before, well, you have the probability of alpha shade to K is equal to N alpha divided by D alpha.
Yeah. So the numerators cancel because they correspond to reaction going in the opposite directions. And so what remains is the ratio of the denominators, which up to some approximation one can factor into something corresponding to the bacterium and something corresponding to the environment. And this something corresponding to the environment involves in particular the concentrations of the various chemicals which play a role in this duplication, because that's what England really does. He does look at an initial state which is one bacterium and a final state which is two bacteria.
What happened with the environment?
And something happens in the meantime, but so it's a bold assumption that one can use detailed balance for such situation. And it's not incorrect. The conclusions that one may take are somewhat, this has to be, these conclusions have to be taken with a little grain of salt because of the everything being equal.
The main point is the decomposition of the alpha on probability on bacteria and environment.
The alpha is, yeah, this I assume that this is a product of two things, which is not unreasonable, but it is an approximation. So, I mean, I spent a lot of time trying to understand this thing because it was apparently exciting. One really rigorous thing that one could say about life. And I'm convinced that the use of detailed balance is really a very good idea. Whether it really says as much as England claims is a little bit open to question. What I did was to try to go from derivation of detailed balance based on stochastic dynamics for everything to something where I assume normal dynamics for the important things. That I think some of the reactions that take place in life are not simply stochastic. Okay, so that's what I wanted to say.